Have you ever, tried to create this brilliant new shortcut or, an optimized system for your workflow, only to find out it actually takes you twice as long?
Oh, yeah, the classic optimization trap.
Exactly. Well, welcome to today's deep dive, because today we're extracting a counterintuitive lesson from a highly specific technical note about Haskell programming.
Right, and it's a fascinating one.
It really is. Our mission today is to understand how a supposed optimization can just, become this massive bottleneck if you use it incorrectly.
Yeah, and the source material here is great. It's from a programmer who was benchmarking a very specific task.
Right? Parsing Chinese numeral characters in a stream of text.
Exactly. And what this benchmark reveals about hidden initialization costs is universally applicable. I mean, whether you're writing functional code or designing a huge microservice architecture.
So let's just set the stage here. What exactly are the two methods being compared in this parsing task?
So the programmer is testing two ways to search for these Chinese numeral characters. On one side, you have a list-based lineal search,
Okay.
and on the other, you have a set-based lookup. Now, conventional wisdom says that checking a list is an ON operation.
Right, meaning it scales linearly.
Exactly.
Yeah.
But a set lookup operates at O1, or, O log n, so it offers dramatically faster retrieval as things scale.
I mean, to make this relatable, a list-based linear search is basically like looking for a specific receipt in a giant unsorted stack of papers on your desk.
Yeah, you just have to check them one by one.
Right. But a set-based lookup is theoretically like having a perfectly organized index filing cabinet. You instantly know exactly where that receipt is.
That's a perfect analogy, and there's a crucial piece of context from the source here.
Oh, right, the pre-calculation part.
Yes, the programmer had previously discovered that pre-calculating this set your filing cabinet is an essential optimization for this to work.
Which makes sense.
Yeah.
But this leads to the central question of the whole experiment. What happens if you don't pre-calculate it?
Well, that's exactly what they wanted to test. They updated their code to see what the performance hit would be if they rebuilt the set on every single character check.
Wait, okay, let me push back on that.
Yeah.
To use my earlier analogy, that means every single time you need to find one receipt, you're buying a whole new filing cabinet.
Pretty much, yeah.
You're assembling it from scratch, putting all the papers into their specific folders, checking for your one receipt, and then just throwing the whole cabinet into a wood chipper.
Yep. That sounds exhausting, right?
That sounds completely insane.
It is, but at the CPU level, that is exactly what the code is doing, and this is why it's such a trap.
Because people hear, sits are faster.
Right. People hear set lookups are faster than list searches, and they just blindly implement sets. They completely forget that constructing the set actually has a massive computational cost.
Because in Haskell, it's not just slapping a label on a list.
No, it typically constructs a balanced binary tree under the hood. Building that tree is an ON log n operation. So you're forcing the system to execute this heavy ON log n operation just to set up a faster lookup.
Okay, so the theory obviously implies this is a terrible idea.
Huh.
But let's look at the actual hard data from the benchmark. Just how bad is the damage?
It's pretty brutal.
Yeah, look at the HTML output from the source. The list-based approach absolutely crushes the rebuilding set-based approach.
Oh, without question. In the best case scenario, the simple list is 11.5 times faster.
11.5 times, that's huge.
It really is. I mean, think about that magnitude. For what is just a simple check, this elegant set solution becomes incredibly destructive to performance when you force it to rebuild continuously.
And what about the worst-case scenario? The notes mention something called the not found scenario.
Right, so that's where the character isn't a Chinese numeral at all. In that scenario, the simple list is still about 5.8 times faster.
Wait, really? Why is the not found scenario specifically so painful for the set?
Because of the asymmetry of the workload. Let's say the program receives the letter A. Before it can even look for A, it has to do 100% of that agonizing setup work.
Oh,
It allocates the memory, builds the whole balanced tree of Chinese numerals, and sets up all the pointers.
all just to find out it's not there.
Exactly. It traverses this beautiful tree, discovers A isn't there, and returns false. It performed maximum effort for a negative result.
Whereas the list approach handles failure incredibly cheaply.
Right. It just checks the first item, checks the second, realizes the byte signature doesn't match, and moves on in nanoseconds. Zero memory allocation.
Which brings up garbage collection, right?
Yeah.
Because Haskell relies heavily on that.
Oh, absolutely. You're allocating fresh memory for a brand new tree on every single character check and then discarding it.
So it just fills up the memory heap with dead trees.
Yes, thousands of them. It forces the garbage collector to constantly freeze the program and sweep away dead objects.
You're basically paying a luxury tax on memory you used for a microsecond.
That's a great way to put it.
But wait, if the list is crushing the set here, how does the programmer actually get the promised optimization of the set without ruining the whole system?
Well, the source text gives us the technical fix for this. For the actual parsing code, the set must be defined at the global level.
Okay, meaning outside the localized parser itself.
Exactly. By lifting it out of the localized function and putting it at the top level of the module, the compiler treats it differently.
So it only has to compute the set once.
Right. You're telling the compiler, hey, this collection of Chinese numerals is static. It's a constant.
And the source notes mention caching it through something called memoization. Let's translate that for the listener.
Yeah, memoization is key here.
It's basically the system memorizing the answer so it doesn't have to do the heavy lifting a second time, right?
Exactly. Under the hood, Haskell represents this top-level set as a thunk, which is just an unevaluated computation.
A thunk. I love that word.
It's a great word. So when the parser checks the very first character, it forces that thunk to evaluate. The system pays the construction tax exactly once.
It builds a filing cabinet once, leaves it in the room, and just uses it whenever needed.
Precisely. Once the tree is built, the compiler overwrites the thunk in memory with a direct pointer to the fully constructed set. It memorizes it.
That's honestly like magic. So for the second character and the millionth character, it just follows the pointer.
Yep. No building, no massive garbage collection overhead.
So the ultimate lesson from the source here is that the intended optimization only works if the usage is correct.
Right. Otherwise, the very thing meant to speed you up becomes your primary bottleneck.
Because modern languages make it so easy to just type, set dot from list. The syntax is so clean.
It is. It hides all the complexity. The developer just sees a function call that promises faster lookups.
They don't see the massive factories spinning up inside their tight loop.
Exactly. They abstract away the hardware and treat memory allocation like it's free.
Wow. So to wrap up this deep dive for you listening, we've journeyed from a simple Haskell benchmark parsing Chinese numerals all the way to this broader realization about the hidden costs of efficiency.
It's a really important shift in perspective.
It is. It shows what happens when we constantly rebuild our tools instead of caching them.
And that actually leads to a final thought I want you to mull over.
Ooh, I like where this is going.
Think about your own daily routines, your own workflows, or, the systems you've built.
Yeah.
Where are you relying on a supposedly optimized process, but secretly paying a massive hidden rebuilding cost every single time you use it?
That is such a good question.
Right. Are you building a new filing cabinet every morning instead of just defining your tools globally?
Honestly, I might be. Something for all of us to explore on our own. Thanks for joining us on this deep dive.